Namaste. Welcome to the last lecture of week 10. We have been talking to you about the physics of nanomaterials. How does the energy drives the formation of nanomaterials and how the energy levels in nanomaterials can be tuned to get new types of nanomaterials, and they have new functionalities and novel properties. We have from the beginning emphasized that nanomaterials are here to stay. As we move towards miniaturization of the devices, high functionalities, you will find new and newer nanomaterials being discovered, and the ones which are already well established being relooked so that when they are taken to nano-sized, can functionalities be introduced in them, and if so, what would those be and how that can be used for various applications. In this, let us today talk about a well known material, and that is silicon. Silicon is one of the most investigated semiconductor material and also as substrate for various other systems. Can new functionalities be introduced in silicon other than taking an intrinsic silicon to an extrinsic silicon and modulating its semiconductor property only? Can we introduce some new functionalities, new response characteristics by tuning the size of silicon, the way the particles are arranged in silicon lattice, and by changing the lattice parameters? Or can we introduce voids? That means, can we make porous silicons and see new behaviors? We will see that these strategies are now allowing us to have a relook at the conventional materials and add new properties and functional responses in them. We will look into two major applications, photoluminescence and photovoltaics, because we are in this week concerned about the use of nanomaterials for energy applications. So, if you look into the contents that we will cover today, you will find we will talk about porous silicon. How does the properties of silicon change as we introduce porosity in a crystalline silicon or a polycrystalline silicon with porosity in it changes its response characteristics, which are being widely exploited for different applications. We will start our discussion on the use of porous silicons in photoluminescence, and then we will move towards the use of nanomaterials, semiconductors which are nano-sized in the area of PV cells, and then we will find out why these materials are becoming so important. So, if you look into a porous structure, as we have discussed in the previous week, that means you are introducing some voids, some channels in the well arranged or array of the atoms arranged periodically. So, then the size of these channels can be modulated. You can go from microporous size channels to nanoporous type voids in these systems. And as we change this, you find that the nature of confinement gets modulated, and as the nature of confinement gets modulated, the electron transport gets modulated and you get different response characteristics. We have seen that as you introduce such porosities, then the interiors of the bulk become accessible for interaction with anything which is intercalating or diffusing in such a substrate. Hence, it increases the effective surface area which becomes available for us to initiate chemical or any kind of exchange reactions. So, due to these pores, you see an increase in the surface to volume ratio, or the specific surface area increases significantly. Now, if you introduce porosity in the structure of silicon, then one of the very interesting properties that get modulated is photoluminescence. And when combined with the semiconducting property of silicon, these materials become useful for photovoltaic or solar cell applications. If you look into the various types of pores, then if you have pores which have the pore diameters less than 2 nanometers, then they are called as microporous. In the range of 2 to 50 nanometers, then they are called as mesoporous, and if you have the pores which are more than 50 nanometers, then they are called as macroporous. And you have different types of materials where such structures are observed, and we have discussed zeolites, we have discussed pillared clays, we have discussed mesoporous materials, and we have also discussed the ceramic based materials which have much larger size pore, and that modulates the property. So, if you look into porous silicons, sometimes you can have systems where you can tune approximately 10 to 90% volume with voids in it. So, you can have 20% voids, you can have 30% voids, or you can have 90% voids. Now, this is obtained by modulating the fabrication processes which we discussed in the earlier part of this course. You can use various types of template based synthesis, or you can modulate the rate at which the nanoreactors would get removed from the reactants, or you can modulate the size of the nanoreactors which gets stabilized in a, for example, mini emulsion system, and then you can go on changing the size of the pores. And obviously, if you introduce such numbers of voids inside the structure, what will you get? You will get low densities, because you do not have the material in that whole volume, and so the densities will be much lower. So, what happens? Let us start with a physical property such as optical property. Now, if you see a PL spectra at room temperature, then you will find that in the bulk it is not observed. But as you move from one structure to the other structure of silicon, then you start seeing that the refractive index of the silicon is directly dependent on porosity. And because of this, strong light absorption occurs in these porous silicons when compared to solid bulk silicons. And the emission wavelength is directly dependent on the pore size. Similarly, you will find that the electrical properties can be tuned by modulating the porosity in them. This happens because when you look at the, let us say, the interfaces which are getting formed, then they have different magnitude of scattering at the pore surfaces, and therefore, the carrier mobility reduces. So, by changing the surface, you can change the electrical properties in such silicons. Because you can have the dangling bonds of silicon and hydrogen groups, you will find that the surface is highly reactive, and if you increase the surface area, that means you have high specific surface area, then their chemical reactivity will be quite high, and then you can use it for sensing or drug delivery. But mechanically, the porous silicon is more fragile and brittle compared to bulk silicon. Clearly, if you have a very porous material, its Young's modulus is bound to decrease when compared to its bulk counterpart. But you can then modulate the mechanical properties by controlling the percentage of voids in them. So, there are properties where the impact of voids is very clear. Hence, porous silicon is finding large number of applications, and in this week we are talking about certain applications like catalysis, energy storage. So, you will find that porous silicon also is being used in such applications. In addition, this is finding very interesting application because it is able to display photoluminescence at room temperature. Hence, what you can do? You can use the layer of a porous silicon that is there on a solar cell, and that would increase the efficiency of solar cell significantly by increasing the light which is absorbed. And if you then want to use the dielectric of the porous silicon as the targeted property which you want to exploit, then you can find that you can tune the porosity, you can change their electrical properties, and hence the dielectric constant can be modulated, and then it can be used as a dielectric for capacitor applications. Now, because of the porosity, the system is able to absorb volume changes during charging and discharging processes. It acts like a sponge, and therefore, they are being used in battery systems where expansion and contraction occurs during charging and discharging processes. So, you need a structure which is able to sustain and maintain its mechanical integrity during expansion or contraction, and therefore, porous silicon is becoming useful for battery systems also. So, photoluminescence is a phenomena where a substance absorbs photons and subsequently re-emits the light. So, you have this process occurring in predominantly 3 steps: the excitation, that is called as photoexcitation. So, there is an excitation photon that drives the electrons from lower energy level, for example, band which is called as valence band, and then taking it to a higher energy level. Here we are taking a case of conduction band, and then you have a non-radiative relaxation, and then you have a luminescence photon coming out when the electron jumps back from the lowest energy level of the conduction band to the highest energy level of the valence band. So, this process is predominantly governed by the energy difference between the ground and excited states and the energy of the exciting photons. Once excited, what happens? The electrons quickly lose some of their energy through the non-radiative processes, mostly heat dissipation. This leads to electrons settling down to a lower vibrational level of the excited state. Hence, when they reach the lowest energy level of the conduction band, then the electron relaxes back to the ground state and emits a photon in the process. So, you have an absorption and then an emission, and this is a Stokes shift. Why? Because due to the non-radiative process, the emitted photon has lower energy and meaning a longer wavelength than the absorbed photon, and you see this Stokes shift. But now you have an emission process, and the wavelengths which are emitted would be directly dependent on the band gap of the materials. Now, if you look into porous silicon, you have 2 things to play with: the size and surface area of the materials. Now, when you take this size of the materials or nanocrystals of silicon below the Bohr radius, the band gap widens significantly, as we had seen in the initial part of this course. Now, the indirect nature of the bulk silicon band gap is therefore weakened, and you get more direct like radiative recombination of electron hole pair. So, directly from conduction band to valence band straight down. So, you have direct like radiative combination of electron hole pairs. And what will happen? The color of the emitted light is dependent on the size of the nanocrystal, because that will decide the band gap of the material which you will be observing. So, you will find that if you have a bulk silicon and then you have a silicon nanoparticle, then at room temperature you will find that clearly you see the impact of quantum confinement, and this causes a blue shift, that is a shift to a shorter wavelength in the PL spectrum, meaning higher energies. So, this concept is then used for various applications, namely photovoltaics, optoelectronics, sensing and biomedicine. So, in photovoltaics, you have it as anti-reflection coatings to trap more photons in the solar cells, and this acts as a down conversion layer which absorbs the high energy photons and re-emits them as one or more lower energy photons, increasing the efficiency of the solar cells, because now you have more number of photons hitting the junctions between the PN or NP layers in a PNP type solar cell. So, now you can use optoelectronic applications of porous silicons. This enables faster on chip communication using light instead of wires. Then you can use for sensing, because porous silicon has higher internal surface area, which becomes more sensitive to environment. So, you can make sensitive chemical and biological sensors, and then photoluminescent porous silicon nanoparticles can act as a trackable agent for bioimaging. If you talk about photovoltaics, what are these? These are the devices that directly converts sunlight into electricity using the concept of photovoltaics. So, you have a semiconductor based device capturing sunlight and converting it to DC power, and then you have lot of solar cells brought together into a solar array connected using a bus bar, and then you get high currents or power output. And then you have a inverter connected to it that converts the DC power from the panels to the AC power for grid connections. So, if you look into a structure, what is there? You have the light falling, and then there is a, for example, a N type layer, then you have the depletion layer, and then you have the P type material. So, in the depletion layer you are having an area which is devoid of mobile charges, because there is a combination of electron and holes. But if you can have energy falling in this depletion layer, the electron hole pairs can then become active again, and electrons will move towards the n type region and holes will move towards the p type regions, and then you can have the current flow. And the electron will move through the external circuit to provide usable electric power, because at the end the overall structure has to be neutral. So, electron will flow back from the top layer and then go in through the bottom current collector, so that both the sides again obtain the state of charge neutrality. So, this is a typical structure. You have the fingers, you have the bus bar, and you have the anti-reflecting layer, and you have the junctions. So, you have the absorber layer, you have the junction layer, you have the back electrical contact where the electron will come back and enter again, so that the structure can again obtain the state of charge neutrality. This is the bus bar where the fingers are connected to, so that you can take all the electrons collected on the top surface, and then when they move through the external circuit, that gives you the current. And when the light falls, it passes through the thin layer on the top and hits the depletion layer, and you get the release of the electron hole pairs. Electrons move towards the n side and hole move towards the p side, because the solar cell is intrinsically reverse biased. So, the bias is driving the potential in a way that electrons will move towards the n side and holes will move towards the p side, and then you can collect this excess electrons through the external circuit and then send it back to the p type layer at the bottom, and you will get both the sides becoming charge neutral again. So, one is the electron transport layer ETL, and the other is HTL, that is the hole transport layer. And this is what the construction of a cell looks like. Now, as you make newer nanomaterials, you can tune their band gaps in a manner that they absorb the visible light more efficiently. You can have these patterning or self arrays being constructed in a manner that they have high absorption, and therefore, you can improve the efficiencies of these solar cells. And that is the typical operation of the solar cell. So, you have an n type semiconductor, you have a p type semiconductor, there is a depletion layer. When the photon strikes, it has to pass through the top layer. So, that has to be quite thin and transparent, resulting in the release of electrons and hole in the depletion layer. Electrons move in the n side and holes move towards the p type, because the cell is intrinsically reverse biased, and you cannot have a material which is charged, and therefore, excess electrons then move through the external circuit, enter through the current collector in the p type, and then introduce the condition of charge neutrality in both the sides, and you get the flow of current. So, you can make different types of nanomaterials, you can make different types of n type semiconductors, you can get different types of p type semiconductors, and therefore, you can get newer types of solar cells, and if you use porous silicon, then it acts as an absorber of the light, which then emits these emissions which are targeted towards the solar cell. So, you improve the absorption at the top layer itself, you provide more number of photons for the release of electrons and holes in the depletion layer, and hence you can increase the overall efficiencies of the solar cell. So, if you look into the polished crystalline silicon, that reflects nearly 35% of the incident sunlight, while if you look into the traditional utilized anti-reflecting coating, that is silicon nitride, they are effective, but they add to complexity and cost. So, what you need, that you need to change this, and that is where silicon is introduced, so that you can have new optical and electronic properties that can help to reduce these limitations which are there in the conventionally used silicon solar cells. You can also have graded refractive index. So, you can tune the porosity, and then you can have changing porosities in different layers, hence their refractive index would change gradually as you move from the top surface towards the inner of the bulk. So, that would minimize the abrupt change that can cause a reflection, and that is why you are now using graded porous silicons. Silicon fabrication techniques are now well established, so they are cost effective. Now, as we said, porous silicon can absorb one high energy photon and re-emit as one or even two lower energy photons in the visible range. This is called as the technique or phenomena of quantum cutting, and you convert energy that would have been otherwise lost as heat to a more useful energy. You can have porous silicon during the upconversion process. So, you have a porous silicon layer at the back of the solar cell. Now, this can absorb two low energy infrared photons and combine their energy to emit one higher energy absorbable photon. So, now you can have high energy photons coming from the back side of the solar cell, where direct sunlight may not be falling. So, clearly now you have seen that you have a new strategy, a new way to tune the nanomaterials and extend their application in the area of energy generation. And like this, there are many more applications where nanomaterials are being used in the area of energy generation, storage and transmission, and that is a subject in itself. But I hope in this week you must have understood that the role of nanomaterials in a very important area, that is energy, is now indispensable, and you will find new technologies, new integrated storage, generation, transmission systems being proposed, which would be highly dependent on new nanomaterials or systems which have been relooked. For example, we have talked about porous silicon in this lecture today, but you can look into more such conventional semiconductors, and now you can easily have an idea how to introduce new properties in such systems and then extend their application to non-trivial areas, niche areas or applications which are for our daily routine. These are some more references where these topics have been covered more in detail and would be useful for you if you want to develop even more understanding about these topics that were covered today. So, I thank you for attending this lecture, and from next week we will start the lectures that would deal with the characterization tools used to study the properties of nanomaterial and also to investigate the response characteristics which are there in these nanomaterials, so that they can be used in various applications. Thank you very much.